Alright guys, so we are getting deep into tensors now. Now in the previous session we found that the stress and strains both can be expressed in the form of a tensor, and this tensor representation gives us a comprehensive way of describing the stress experienced by the material and the response offered by the material. Unfortunately, we also found that the meaning associated with the indices of the tensor vary with the coordinate systems, the frames of references, and our material that we use in our engineering application. They unfortunately include too many frames of references. So ideally, we have to come up with a way of representing the stress tensor in such a way that this tensor is rather independent of the frames of reference. When I have a continuum with 1000 grains, with meaning 1000 different frames of reference, then in order to describe the stress experienced by this continuum meaning this block of material, I do not need 1000 tensors. I need to come up with a way to express these 1000 tensor into a single tensor which is independent of the frame of reference. That is our objective towards which we are going to march. In order to reach that objective, it is rather vital to start by understanding the relation between the two frames of references in order to achieve that. So we have a greater target to achieve. We have a huge march before us. So we will break this entire journey into smaller ones. The first step is to achieve to arrive at a way of expressing the tensor which is independent of the frame of reference. To arrive at that overarching goal, we will first begin by understanding the relation between the two frames of reference. So in this case, what we are considering is two different types of coordinate system. We will begin with a smaller steps, with the baby steps. We will try to understand the relation between these two coordinate systems. So what we have here is we have two coordinate system, the Cartesian coordinate system that is with its basis x and y, and we have our spherical coordinate system which is described by r and theta. Now a point A here, it is described using r and theta, and of course it can also be described using x and y. Now we have superimposed the r and theta and x and y here in this representation. So this allows us to relate our x to r and theta, and our y, which is the basis of our Cartesian coordinate system, to r and theta, again the basis of our spherical coordinate system. And vice versa, we are able to express r using x and y, the basis of our Cartesian coordinate, theta that is associated with spherical, to x and y, again the basis of our Cartesian coordinate. Now what we want to find is, we want to find how we can describe the relation between these two coordinate systems. Again, not the basis of the coordinate system, but these two coordinate system. Now before we proceed to that, the reason I'm rushing through this is because I guess many of you are familiar with these coordinate system, and if you are not, it's just I'm representing a point using r and theta. So I have to go a radius r, and with respect to a specific angle, so r and theta describes that, the point A, and the same point A I can describe it by moving x times along in this direction and y times along in this direction, so I end up reaching the same point. So r and theta, x and y describe the same point, so I can come up with a construction like this, and using this construction I'm able to arrive at the relation between x r and theta, y r and theta, and also the relation between r that describes x and y, and theta that describes, or that is represented in terms of x and y. So from this representation of a point that is described using both x and y and r and theta, I construct a right angle triangle, and using trigonometry I am able to express r in terms of x and y, theta in terms of x and y, and vice versa. Now what we want to do is, we want to understand not the relation between these bases, but the relation between these two different coordinate systems. How is Cartesian coordinate system related to that of or how I can easily describe the relation between the Cartesian and the spherical coordinate system. So in order to do that, I'm going to consider a parameter that is known to me in one coordinate system. In order to describe the relation between the two coordinate system, I'm going to consider a parameter that is well known to me in one coordinate system. I'm going to consider a parameter that is well known to me, let's say, in spherical coordinate system. This parameter is known to me, meaning I can easily understand it, it's known to me. So such known parameter for me in the spherical coordinate system, let us assume that I'm considering the parameter r. This parameter r it makes absolute sense to me. I don't need any further description for understanding r in the spherical coordinate system. When I will say r and give a specific value, I'm able to understand it. I don't have to need any further assistance for me. I'm able to understand the meaning of r in the spherical coordinate system. Alright, so r is nothing but r might include all the points that are in the red circle here. So I'm able to understand r in the spherical coordinate system. Wonderful. Now this r that is known to be in the spherical coordinate system, I'm going to represent it in the Cartesian coordinate system. The r is known to be, and this known r, I'm going to express it in the Cartesian coordinate system. Now what I'm going to do is, I'm going to replace the basis of the Cartesian coordinate system with that of the spherical coordinate system. So there is a known parameter, a parameter that is known to be in a specific reference. I'm expressing that parameter in an unknown reference that is in a Cartesian framework. And now, without disturbing this parameter that is known to be, I'm just replacing the framework in which I'm describing my known parameter, the coordinate system in which I'm describing my known parameter. I'm replacing the frame of reference from Cartesian to that of the spherical. Now when I'm able to recover my known parameter in this replaced spherical system, then there is a specific relation between my Cartesian and the spherical coordinate system. Let me repeat. I need to repeat it because it might be a bit evasive. So I'm considering a parameter that is known to me in a spherical coordinate system. I'm aware of it, I understand the meaning of it. Now I take that parameter, describe it in the Cartesian coordinate system, another coordinate system. And without disturbing the parameter, I'm just replacing the coordinate system with the spherical coordinate system. Now, if I'm able to recover the meaning of the original known parameter in this replaced spherical coordinate system, then there exists a specific relationship between these two different coordinate systems. So let us do that. Now, r, which is known to me in the spherical coordinate system, is expressed in the Cartesian framework. R, known to me in the spherical coordinate system, is expressed in the Cartesian framework in this step 1 here. Now without disturbing my r, I'm replacing my or rewriting my Cartesian coordinate systems in the spherical coordinate framework. So without disturbing r, I'm replacing my Cartesian in the spherical framework. So when I do that, let us do that by substituting these expressions here. Let us start with x and y and represent r using x and y, and let us replace x and y with r and theta. So that is what it means. I'm writing my r using x and y. So I'm describing my known r using x and y. And then as a next step, I'm replacing my r or my x and y with r and theta. And ultimately, I should be able to recover my known parameter here. Let us see if we are able to recover it. So I'm writing my r using my x and y. I can write it as this. My r using x and y can be written in this way here. And this x and y, in the second step, I'm rewriting it in terms of r and theta. So I have to bring these here. And when I merge these two and then rewrite my r in terms of r and theta through x and y, I end up having an expression like this. Alright. So I start by rewriting my r or writing my r in x and y. And now I'm replacing my x and y using r and theta. So I bring in these two expressions and rewriting this entire expression, entire term using r and theta. So when I do that, I end up recovering my r. Wonderful. I take a known parameter, express it in another frame of reference, replace that frame of reference with the known one. I'm able to recover my parameter. Wonderful. Let us try to do the same with theta. I can write my theta in terms of x and y. So this is the expression that I get. Theta written in terms of x and y. So this is written in an unknown frame of reference. And now I'm replacing the x and y with r and theta, something that is known to me. So when I do that, so expressing x and y in terms of r and theta, that is here and here. These are known. These relations are known to me, and ultimately when I do that, I end up recovering my theta. So basically there are known parameters, I'm expressing it another frame of reference, and now I'm swapping the frame of reference. I'm able to recover my known parameter. So when this is possible, then these two frames of reference are referred to be inverse of one another. If I'm able to recover a known parameter by swapping in these frame of reference in which they are originally expressed, we refer to them as inverse frame of reference. So what we mean by inverse frame of reference is I will be able to express a given parameter or translate a given parameter from one frame of reference to another frame of reference using a function. When I do the inverse of the function, I will be able to rewrite that parameter in the other frame of reference. Meaning, if I'm able to express, say, r in the frame of reference of x and y, and I want to change it to r and theta, I perform an operation. I want to express it in terms of r and theta. I perform an operation, a numerical operation to it. And when I perform the inverse of the numerical operation, I will be able to get back to my original r. So that is what the inverse relation between the coordinate systems mean. So f here indicates a numerical operation. One numerical operation allows my entity or my parameter to be described in another frame of reference. Let's say y frame of or v frame of reference, from u to v frame of reference. When I do the inverse of the numerical operation, then I'll be able to express the same parameter from v to u. I'll be able to bring back the expression of the parameter from v to u. So I do an operation, express a parameter in a given frame of reference. And when I do the inverse of it, get back to its original form. When this is possible, just by inverting the numerical operation, I'm able to do this is what we refer to as the inverse relation between the two coordinate systems. Now in this case, we were able to prove the inverse relation because the relation between the different bases were known to us. We were able to prove the inverse relation because the relation between these variables, the relation between the bases and of the different coordinate system is known to us, and therefore we were able to prove the inverse relation between the two coordinate systems. Now what if the inverse relation is not known to us? So one way of showing that two coordinate systems are inverse of one another, even when the relation between its bases is not known to us, is by considering this derivative here. Let me repeat. We want to prove one coordinate system is the inverse of another coordinate system. We proved that the Cartesian is the inverse of spherical, and in order to prove that, we used the relation between x and r theta, y and r theta, r with respect to x comma y, and theta with respect to x comma y. So we used all these relations in order to prove that the spherical and the Cartesian coordinate systems are inverse of one another. What if these relations are not known to us? Now when these relations are not known to us, it is still possible for us to prove that two coordinate systems are inverse of one another. Again, I hope you understood what the inverse mean. Now when you want to prove these two coordinate systems are inverse of one another without knowing the relation between the bases, you begin by considering the derivative of one coordinate system with respect to another coordinate system, the derivative of the Cartesian with respect to spherical. So that is what is being done here. The J1 is the derivative of the Cartesian coordinate system with respect to spherical. So what you see here is change in x with respect to r, change in x with respect to theta, and change in y with respect to r, and change in y with respect to theta. So this is something called as a Jacobian matrix. So we are considering the derivative of the Cartesian with respect to spherical. Now also it is possible for us to cook up with another Jacobian matrix wherein we are considering the derivative of the spherical coordinate system with respect to of the Cartesian coordinate system. But nonetheless, before going into that with that Jacobian, let us try to find out the values of these Jacobian here, or values of these entries here. So we have the relation. Again, we are using the relation. You will see why in this case it is important, but this understanding is generalized. So we will use the relation here. So we know how x is related to r and theta and how y is related to r and theta. So we can use these relation here to find out these individual entities. And when we use those relation and find out the individual entities, you end up with the square matrix here. Now we can consider the second Jacobian, wherein the derivative of the Cartesian or the spherical coordinates is determined with respect to the Cartesian coordinates. So the change in the spherical coordinate with respect to Cartesian is what we have expressed in this second Jacobian J2. And again, we will use the corresponding relation to find the entries of these Jacobian. pardon me, it is rather my video here overlaps with this relation here, but I guess you are kind of familiar with the relation. So essentially what we are doing is we are trying to use this relation and find the individual entries of this Jacobian here. Now we have two Jacobian matrices that one talks about the change in the Cartesian with respect to the spherical, the other change in spherical with respect to the Cartesian. Now we want to relate these two Jacobians, and unfortunately one is in r theta, the other is in x and y, and of course we will bring in this relation between x in terms of r and theta and replace the second Jacobian with r and theta. So we have one Jacobian talking about the change in Cartesian with respect to spherical, the other Jacobian talking about the change in spherical with respect to Cartesian. We want to play around with the Jacobian, so we are changing the Jacobian and expressing the Jacobian 2 in terms of r and theta. Now when you consider the product of these two Jacobians, we find that the end product of these two Jacobians is an identity matrix. So essentially what we found, or rather what we find here in this case is, we already have established through the known information, we already have established that the Cartesian coordinate system is rather the inverse of the spherical coordinate system. The Cartesian coordinate system, we have already proved that the Cartesian coordinate system is the inverse of the spherical coordinate system. Now what we are trying to achieve in this derivation, so this we were able to prove because we know the relation between x in terms of r and theta, y in terms of r and theta, r in terms of x and y, and theta in terms of x and y. These relations allowed us to prove the inverse relation between the Cartesian and the spherical coordinate systems. Now in the subsequent analysis what we performed, in subsequent derivation by involving Jacobians, what we showed was when we are able to find the Jacobian of these two coordinate systems, and when we multiply the Jacobian of these two coordinate systems, when the product of these two Jacobian gives an identity matrix, then we can say that these two coordinate systems are inverse of one another. So we already proved that these two are inverse of one another, and we consider the Jacobian of these two coordinate systems, and these product of these two Jacobians gave us this identity matrix. So what it essentially means is that when our coordinate systems are inverse of one another, the product of their Jacobian is going to be identity matrix. So since the inverse relation is already known, now what we found is the product of their Jacobian is going to be identity matrix. Now we can reverse it. So when this is known, when the inverse relation is known, the product of the Jacobian is identity matrix is what we found. So this is known and this is what we found. On the other hand, if we are able to prove that the product of the Jacobian is identity matrix for two different generic coordinate systems, then the corollary of this theorem is, what we can know from that is, these two coordinate systems, let's say I1 and I2, these two coordinate systems are inverse of one another. Now this study here showed that when the coordinate systems are inverse of one another, the product of the Jacobian is going to be identity. Now using this understanding, we can say when we can find the product of two Jacobian that pertains to two different coordinate systems, and we find that the product of the Jacobian is identity matrix, then we can safely say that these two different coordinate systems are inverse of one another. This understanding, we are now going to adapt it for the generic frames of reference, and then we are going to see if they are inverse of one another or not. Goodbye guys.